Welcome to Mineri's seminar. It's my pleasure to introduce Professor Yang from Biomedical Engineering. He's an associate professor. He received his master's and PhDs from University of California, Santa Cruz in 2007, 2010, respectively. His interests are in implantable devices, AI, and neuromodulation. He brings a very unique perspective because he's not only a man of words and equations, but he is very much interested in commercializing and moving some of these technologies to companies that they can make these things available to users who need these systems. So without further ado, please start.
Okay, thank you very much, Nikos, and thank you very much for attending this presentation. So today I'm going to talk about brain-machine interface. So please feel free to stop me if you have any questions. So my lab primarily works on integrated circuits, algorithms, and electrodes to interact with the human nervous system. So on the left side, you would be able to see an integrated circuit chip we have developed. So here's a little bit introduction about the neuron signals. I know the majority of you guys are not from the neuroengineering, so I'm just going to give a brief introduction about the different type of neuron signals. So in general, there are both brain signals and the nerve signals. So the brain signals, it has an amplitude about 50 microvolt to 1 millivolt. And they were both a single unit activity and some field potentials. In case we have a single unit activities, we would be able to see spikes. When we talk about the recordings from a peripheral nerves, then the signals would be much smaller, and they can have a variety of different shapes. And in general, nerve recording is more difficult because the nerve recording requires ultra-sensitive devices. The advantage of nerve recording is it avoids brain surgery, because when we do invasive brain recording, we really have to drill a hole through the skull and implanting the electrodes into the target region. So, so I have been as an assistant professor, then associate professor for 10 years. So in the first 7 years, my lab has designed 12 integrated circuit chips to record, analyze, and modulate the neuron signals. I joined the University of Minnesota in 2015. So after we came to Minnesota, we started to build a medical system based on the work we have done. So for example, as you can see on the two images here, our peripheral nervous system PNS-based brain-machine interface has already enabled the patient to mind playing video games. So the patient in this case needed to take a surgery. They will implant the device to interface with their two peripheral nerves. And after the surgery and after all the training, we asked our patient to say, how do you think about the technology? What would be the biggest application? In this case, our patient said is video games. So he really thinks it's cool to play video games. I'm going to show you more videos, what's going on. So right now, the technologies we have developed at the U has enabled the two human studies. One of them is the PNS brain-machine interface, peripheral nervous system-based brain-machine interface, to restore the lost functions in amputees. So far, we have 10,000 hours implantation time in human subjects. We have done 6 patients up to today. And the other clinical study is an adaptive deep brain stimulation therapy to treat the patients with Parkinson's disease. And we have received an IRB approval to test up to 10 patients. And the patient recruitment is a little delayed due to the COVID-19, but it's on the way. So today's topic would be brain-machine interface. So I would like to take this opportunity to share my own view. That is the robotics and neural technologies, brain science, when the three components combine together, we really be able to engineering a new hand for amputees, make their life a lot better. So I think I have explained some background information. So in the next few slides, I'm going to show you videos. So when we talk about the brain-machine interface, then we need to evaluate how good the brain-machine interface is. So in 1950s, there was a message. Let me see. You need a candidate for Parkinson's evaluation. Yes, we do need a Parkinson's patients. And so I'm going to answer the questions maybe at the end of the presentation, because I just realized that this is hard to look at the questions at the same time unless you tell me. Let me see. Okay, thank you. So there was a Turing test established in 1950s by the very famous British scientist. Basically, in his test, it was a test to evaluate whether the machine intelligence exceeds the human intelligence. Basically, a person is communicating with an agent. If based on the communication, the person is not able to tell if the agent is a man or machine, we call whatever machine can pass that kind of a test intelligent machine. So here, maybe let's do a similar Turing test here. So in the next two slides, I'm going to show you two videos that shows the finger trajectories of both hands. So the videos could come from two types of people. One is the videos would come from a normal person, just like you and me, who have normal hands. So that person, in the case, would wear a pair of data glove. So the data glove would be able to track the joint positions and continuously, and later we can play the joint positions over time. So the second scenario is the video is from a transradial amputee who lost one hand. So the subject intends to perform mirrored hand movement. Of course, the good hand is still tracked by the by a data glove. Then the artificial hand is based on neural recordings recorded from his peripheral nerves, and then being displayed. So let's take a look. So this is the first video. Can you guys see whether the video is from a normal person or from an amputee? Okay, so let's look at the second video.
Yeah, why don't you show us both? So...
Yeah.
The second is the amputee.
Okay, Nicholas, you're certainly right. And the first one is also from an amputee too. It's from the same object. They're from the same subject, I'm sorry. So basically the difference is the first one is 10 degrees of freedom motor decoding, which we do not include the abduction channels. And in the second video is 15 degrees of freedom. We have the abduction channels included. So in many cases, it's very hard to tell. So let's give a little bit more introduction. So what is required to decode the finger trajectories? I would say a lot. First of all, the human hand is a very complicated organ. It has 27 degrees of freedom. So if we assume each joint has 256 gradations, and we talk about 20 frames per second, then it's actually 4,000 kilobits a second information that's needed to be decoded from the nervous system. And if you look at the state of art brain-machine interface based on brain signals like EEG, or based on other, based on muscle signals, or based on ECLG, So it can only produce 6 bit per minute information. That is equivalent to 1 bit per second. So it's far insufficient to support the motor decoding here. And currently, the current neuron prosthetic device used by operating amputee patients in general is based on EMG signals. EMG signals or muscle signals, and it can provide 1 to 4 degrees of freedom. So the hand movement is the hand movements are pre-programmed. So the user can select one of the movement patterns at a time. Typically, they have like say 7 or less than 10 programmed patterns, and the user can select one pattern, and that pattern will last for a few seconds. Then after that, the user can select another pattern. And despite a simple function, prosthetic hand our patients use usually is going to cost the insurance about 50,000 to 150,000 US dollars each. In the past 20 years, there were very sophisticated robotic hands that have been developed. In particular, there were multiple hands developed by the DARPA from a few DARPA programs. And in our view, a critical gap right now is we need a technology that can understand and decode the human subject's motor intention, thus to connect the human brain and a robotic hand or anything else. Then that kind of a hand would be more useful. So the motor intention, one thing I would like to mention, that is the motor intention is from the brain circuits, emerges from the brain circuits. So the mind reading technology here has to touch the nervous systems. The typical data I mentioned, the EEG data or muscle data, are just not sufficient in this case. So here's a little bit of physiology. So there were 5 major peripheral nerves in our arm, and including the axillary, muscular, cutaneous, median, radial, and ulnar nerves. And because our focus here is we wanted to restore the lost motor functions, including the individual finger controls. Therefore, we decided to implant the device to interface with the median nerve, radial nerve, and the ulnar nerves. The median nerve is the successful decoding of the median nerve signals would allow the subject to control the thumb, the index finger, the middle finger, and 50% of the ring finger. The ulnar nerve would help the subject to control the pinky finger, 50% of the ring finger, and a small portion of the middle finger. And the radial nerve is more complementary to the median nerves. So far, we have tried all the 3 nerves. So nerve recording is a very difficult problem. In fact, multiple DARPA program managers mentioned it's a DARPA hard problem, primarily because the nerve neuron signals are very small. It's about 10 to 100 fold smaller than the brain signals. It requires a device with a noise floor around 10 to minus 17 to 10 to minus 16 volts square per hertz. That's very, very low noise floor. And secondly is within each nerve, there are thousands of fibers, and each fiber is connecting to a different target, and the fibers are serving as a multiple bridges or signal pathways that connects the brain and the ending organs. So that kind of a connection network is very complicated. So when we intend to record the signals from the nerves, it's very hard to resolve signals to individual sources, to individual fibers. So that's one of the challenges. Some other challenges is like the motion artifacts and interferences. The signal, like I mentioned, are very small in microvolt range. And the motion artifacts we have can be 1 volt. And because we talk about the device the patient is going to use, right? It's not in lab settings. So the interference and the artifacts are much, much larger. In terms of a scientific contribution, so far, one of the contributions our lab has made is we have developed an ultra low noise recording device. So we have provided a new theory and the circuits to remove the one type of thermal noise. And secondly is we have developed a switched capacitor circuits theory to support the analog operation. As a result, we could reduce the artifacts before ADC. So here's the neuron amplifier front end. I'm not going to talk about the circuits as much. So let's take a look at the earlier stage experiment that we did. So in this experiment, so if you look at the images, this is taken from the microscope view. As you can see, this is the one peripheral nerve of a guinea pig. So we placed the stimulator from the foot side on a sciatic nerve, and we placed the 5 electrodes on the sciatic nerve on the spinal cord side, right? Then we perform electrical stimulation from the foot side, and if we're able to record the neuron signals, then we would see the neuron signals would propagate from on the nerve, probably propagated from the stimulator all the way to the spinal cord, according to this experimental setup. So here are some experimental data. So each one trace is one stimulation. So we performed here, for example, we have to show you 10 different stimulation tries. So each time we would see the stimulation artifact. Because the stimulation artifact in this case is produced by electrical field, and we know electrical field propagated within the body at the speed of 9. Therefore, we do see there is no delay between the channel 1 and channel 2 recording. That is consistent with our expectation. Then we could see there was some signals where the 2-channel recordings has some microsecond delay, about 300 microsecond delay. Based on the spacing among the electrodes and the amount of delay we have, we calculated the propagation speed is about 20 meters per second. And given the nerve has been elevated, it's in a colder temperature, so that kind of a speed is quite reasonable. So we think it could be A beta or A delta neuron signals. Then we also see some signals which are not propagating. Later we need to figure out what are those signals. However, there is one bigger puzzle we had. We have tried the experiments for many hours, and we always see the signals propagating from the spinal cord to the foot instead of from the foot to the spinal cord. That's weird, right? Because if we stimulate the nerve, we expect the signals propagating from the stimulating locations all the way along the nerve, not the other way. So because of that, we have been thinking about the possible explanations until we met a pain doctor. So we collaborated with a pain doctor, Winfield Rabe. So he explained to us what's really going on. So basically, when we're electrically stimulating the sciatic nerve, so both the motor and the sensory nerves are activated, fibers are activated. So the initial activation will be very fast and will be buried by the stimulation artifacts. So what's going to happen is the sensory nerve is being activated and it's propagated from the stimulation location all the way to the spinal cord. Then from the spinal cord, there were 2 pathways. One is a direct coupling to the motor pathway. The signal propagate from the spinal cord all the way to the foot. And the second pathway is the signals go through some interneurons and then activate the motor fibers. So therefore, if everything's right, we should be able to see 2 groups of motor signals propagating from the spinal cord to the foot. Okay, so if that is the case, then our experiment data makes a lot more sense. So we have the initial stimulation artifacts. So the motor fibers and the sensory fibers are activated at this moment. Because of the stimulation artifacts are much larger, therefore they would mask the initial neural activities. So then the signals are propagated all the way to the spinal cord, and then later, then after that we start to see signals propagating on the motor fibers. So when the signals reaches the foot, the muscles, then we start to see the muscle twitch. Because the muscles are outside of the nerve, right? So any signals produced by the muscle will propagate at the speed of 9. As a result, we don't see any propagation delay. It's just out of phase, 180-degree phase shift. So that's reasonable. And after that, like I said, there was a interneurons which can produce the second pathway to activate the motor fibers. Therefore, we see the second group of neuron signals. So of the discussion with pain doctors, we feel a lot more confident about the initial in vivo studies results. So from the study, we realized that we're able to get not only the compound action potentials, we also are able to get signals from individual fibers, at least individual fascicles. As you can see, this is the nerve cross-section, and within the nerve, there were so many different groups, bundles. Each bundle is a fascicle, and within each fascicle, there were so many fibers. The fact we're able to get classifiable neuron signals, meaning we're able to get a single type of activities. And we have repeated our experiments on both the sciatic nerve and the vagus nerve, autonomic nerve, to confirm the study. So after the animal studies, then I started to call my medical collaborators. Then we started to prepare to translate the study into a human, to get the technology into human experiments. So we started to prepare the experiments with cadaver and also with monkeys. And so the collaboration is with a physiologist, Edward Kiefer, and a neurosurgeon, Jonathan Chen, in Texas. So here is of the multiple years preparations to understand how to do this type of surgery. So you can take a look how the implantation surgery is done. So here is an actual human subject, and he was alive, and he's alive. And we'll talk about the implanting the electrodes into his ulnar nerve. So this video is a little too long, but that's roughly tells you how to do the implantation surgery. And that's the electrodes being implanted into the human nerve. So one of my collaborators, Edward Kiefer, so he is very good at the electrodes. He was a pioneer in making carbon nanotube electrodes, so things about 15 years ago. So that's the electrodes we have designed. There were both the live electrode portion and the cough electrode portion. I'm going to explain the electrodes later, but as you can imagine, the electrodes are implanted here. For the initial study, we're connecting the electrodes out to interface with the electronics. So after we have done the experiments and the patients being recovered from the initial surgery, then we're trying to assess the signal quality. Like I mentioned, it's very hard to record the neuron signals from the peripheral nerve. So what we have done here is we grouped the electrodes into two. One group of electrodes are connected to a state-of-the-art repo grapevine system. That's, to our knowledge, the best recording system up to today. And the other group of electrodes are connected to the device we have built. So obviously, you can see our device has much less noise. And to confirm the observation, we switch the two groups. Then we switch the group, and we're very confident our device has a decent noise characteristic, outperforms the state-of-the-art repo system. And it's fortunate that my wife is a computer scientist, therefore she helped us to develop the decoding algorithms. So if you are interested in the decoding algorithm, you can either refer to our paper or talk to her. So I don't have enough computer science training here. So, but I would be able to show you how the human nerve data would look like. And here we ask the patient to perform different patterns. And you can see the low frequency neuron signals and the high frequency neuron signals associated with the patterns. And we talk about the four group of signals, the ulnar nerves and the median nerve, two groups. And then within ulnar nerve is grouped into two because some fibers, some locations are more, we can get the motor fibers. And in some other locations, we get the sensory fibers. Therefore, we typically implant 4 electrode shunts into each patient. And if we zoom in the low frequency and the high frequency the signals to actually see what's going on. You can see that's how the low frequency signal would look like, and what high frequency signals would look like. So one thing is what I mean high frequency neuron signals is not gigahertz signals. I'm referring to signals up to 5 kilohertz. When I refer to low frequency neuron signals, I'm talking about signals up to let's say 150 hertz. So we also analyze the interspecies interval, and we found out that there was a clear refractory period of a few milliseconds. So that is consistent with our understanding of the physiology. And also we identified that there were neurons both excitatory and inhibitory. So that's also good news. So then we used the data to perform offline decoding, and by using our devices versus using a repo system, you can see the decoding accuracy is very different. With a repo system, the VAF score, VAF is shorted for variance accounted for. The score is about 0.1. With our device, the VAF score is about 0.9, and a perfect hand has a VAF score around 1. So here, we're also trying to assess the signal quality on coffee electrodes, on intravascular electrodes. So the coffee electrode, meaning we have the electrodes wrapped around the nerve, so therefore it's going to cause less damage to the nerve. If we talk about intravascular electrodes, it's meaning we're inserting the electrodes into a nerve. Of course, the electrode here would be very small. It requires very good surgeon to perform the surgery. Fortunately, our surgeon and the physiologist are both very good to do this thing. They have spent, I think they have spent multiple years to perfect the surgical procedures and techniques, probably practiced on 300 to 400 reps. So here's the offline decoding results. So by analyzing the data, we found out that we are able to track the joint movement reasonably accurate. Okay, so that's basically the preparation. What's really important is we needed to, it's not like through offline analysis, we show we're able to decode the joint movements. What we wanted to do is to give our amputee patient a new hand. So then we switched to work on online motor decoding since 2018. 3 years after I joined the University of Minnesota. So up to today, we have tried multiple patients. So let me talk about some challenges. If we talk about how are we going to do the online motor decoding. So one of the challenges, the model longevity is just like the average person would have a limited lifespan. And in this case, the neural model would have a lifespan too. So in the BCI literature, it's well understood that a trained model cannot last for more than a day. Typically only lasts for a few hours. So if you want to do the experiment, to do a demo, you have to connect the data immediately and train the model immediately and perform the experiment on the same day. If it's the next day, it's not going to work. So that's one of the challenges in BCI model. The reasons there were multiple reasons caused the limited model longevity. But if you're interested, we can discuss it later. But here, in our case, we want our amputee subject to be able to utilize their hand every day, every moment, right? So likely we're going to connect the data on one day or maybe on 1 week because we may need a lot of data. Then we train a model, a personalized model. So it usually takes us about 2 weeks or 3 weeks to train a model. So you may see why you cannot train the model fast. That is because it's very hard. When I talk to my students and our scientists to say, we want this model to be done in 2 weeks, they usually feel, wow, that's a lot of work. It's not easy, right? So let's say we trained the model in 2 weeks. We did the experiment for a week. Then when the patient is able to use the hand, we talk about we use the model connected 3 weeks ago, the data connected 3 weeks ago to train the model. So that requires the model longevity to be at least 1 month. So that's one of the challenges. The second challenge is the noise. So in offline experiments, there is no robotic hand. In online experiments, there is a robotic hand. So that robotic hand can create a lot of noise too. For example, it requires many ampere currents to drive a robotic finger. While if we talk about the current passing through an electrodes, I mean, we are using electrodes to sense neural signals, right? The current is on the order of a picoampere. Just imagine the difference from ampere to picoampere. So any imperfection can just kill the model. And thirdly, so when we ask the patient to perform the training, it's unrealistic to ask the patient to be trained every day, right? Nobody's going to use that. We typically ask the patient to come into our lab once a month. And for each visit, we would book the hotel for him for 2, 3, or 4 days. So that's all. So in that case, there was a very limited amount of training patterns we can possibly do. While the patient is expected to use their hand in their daily life to do a lot of things. Therefore, the model we have here needed to work on seeing the patterns, on seeing the scenario. So that we talk about generalized AI, that's one challenge. The second challenge is in offline experiments. We could have access to data happened before, after, and during the movement, right? So it's for scientific study. Well, if we talk about want to make a prosthetic hand, then we could only make decisions based on the data we have collected before that moment. So therefore, the logic is strictly causal. And we have to factor in the latency into consideration. So it's a lot more challenge. The fourth challenge is the portability. And when we doing offline experiments, we can afford to use GPU clusters to do all the training. We even use a supercomputing institute facility to do the training. But here, everything has to be portable. So that's just the 4 challenges. Anyway, we started this study 2.5 years ago. So far, we have tested with 3 transradial amputee patients. Transradial amputee means that amputee subject lost the entire hand at least. Some lost their forearm. So for each patient, we have implanted the device 1 to 2 years each. And we have designed 8 to 16 electrodes per shunt. And we put the 2 shunts per nerve. And each time we select the 2 nerves from the 3 nerves I mentioned, the median, ulnar, and the radial nerves I mentioned. So our goal was to implement the first neuron-based prosthetic hand with individual finger control. So that was our first study. After multiple hours, actually multiple days, we finally got enough data to decode signals on the subject ulnar nerve. Like I explained, and also the figure illustrates here, the ulnar nerve controls the movement of the pinky finger. So therefore, our subject become able to control the pinky finger. And we asked the subject and my graduate student to play a video game together. So he just controlled the shooting. That was easy. So here I'm going to show you videos. That was 2 weeks later. Then again, we just decoding the finger movements based on the ulnar nerve. As a result, you would only be able to see the ring finger and the pinky finger.
How does it feel just controlling these?
The ring finger feels real easy, real natural.
Very natural.
Yeah.
What about the pinky? Is it more difficult?
It's just getting used to it, I guess. You know, trying not to overpower other stuff.
But this is the same model you were using 2 weeks ago. Is it the equivalent effort, do you think? I mean, does it feel about the same?
It feels about the same.
Okay.
You know, from what I can remember.
All right. Awesome. Thank you.
So as you can see, the subject imagines what he wants to do. Then the signals are being recorded from his ulnar nerve. So you could see the display here. The bottom traces, or actually the 8 traces are from his ulnar nerves, and the signals are being analyzed in real time, being feedback. And you may see why there was no latency. That is because we predict his intention instead of decoding the intention. And if you have questions, we can get into that aspect later. So then after the initial success, we did more work with the patient for another month. After that month, our patient we are able to successfully decode the signals from his median nerve as well as the results, or the patient can control all 5 fingers. So on the left side is a video where our patient is mind playing a video game, Far Cry 5. So he was driving a helicopter here. He's driving a helicopter here. And trust me, there is no wire connection between him and the computer. There is yeah, you can take a look.
Right.
Wow.
Okay.
Cameron, you are controlling the helicopter left and right.
The middle or moving forward. What you cannot press.
Oh, you are moving forward.
No, I'm controlling it. Now you're moving forward. Now left, right.
What else the bird do?
Oh, your tongue will be shooting.
So this subject, actually multiple subjects are from the military. So therefore, you can see another video I'm going to.
Wow, now it's actually trying to do it.
So our subject, he wants to, so basically after he realized that he become able to control individual fingers. So one of a generalized pattern he would like to do is to show middle finger. So that's cool. And we never have the AI model to train this pattern. And after the first, okay, he spent a lot of efforts to finally be able to show middle finger. Then after the initial success, the subsequent tries is just very natural, easy. It's just like a newborn. Once the newborn understands how to walk, then it becomes a lot more natural and easy. So here is another video to show.
Now. Okay, so I'm going to move the pinky finger first. I'm going to move the index. I'm going to move the middle finger. I'm going to move the ring finger. Now I'm going to move the thumb. Now I'm going to make a fist.
So basically, as you can see, he tells you what he intends to do. Then the hand moves accordingly, the finger moves accordingly. There was no latency because, like I said, we're based on the signals propagating within his peripheral nerves. So we intended to predict what would be his motor intention. The prediction accuracy is pretty high and pretty, yeah. So another interview.
Do you have truly independent finger control, not like the grasp patterns that are programmed into your...
Absolutely. This is nothing like a grasp pattern. This is, you know, I think with training for myself and then learning models like this, I can get back to a natural hand movement.
Is it pleasurable playing with it?
Oh yeah.
Okay.
It's just really cool.
Okay.
Like this is crazy cool.
So just imagine when someone is able to mind control something. You want a cup of orange juice, then the orange juice will be delivered to you. You want to go home, there will be a Uber car waiting for you to go home. That's very cool. So our patient was shocked, actually cried as well, to be able to control individual fingers. And to our understanding, this technology is the only one in the world right now can allow a subject to control individual fingers, in particular in free will. Basically, do whatever you want to do. So, okay, so far I've talked about some of the work related to motor decoding, but as you can imagine, after losing a hand, after the amputation, there were other things. There were other things the patients would need to face. For example, there was a survey among the subjects who used the prosthetic limbs and later they decided to not use it. 85% out of the 85% of those said it's because of lack of sensation. And today, robotic hand is like a cold piece. There is no sensation. They don't feel that the hand is part of their body. As a result, they decided to not use that hand. It's kind of a less intuitive. Just imagine you cannot feel from your hand, then you would be, that kind of feeling would be horrible. The second thing is they would feel severe pain. About 50% of the people who went through amputation would have a residual limb pain. Some of them can have a severe residual limb pain. Like one of the patients we worked with went through, he just lost a few fingers initially, and later he went through 13 surgeries to cut the entire not in part of the forearm, the entire hand, because of the severe pain, extremely painful, and it cannot be treated, extremely painful, but cannot be treated by current medication. So in order to make that happen, for example, to deliver the sensation to our patients, basically our patients to consciously to create some artificial sensations, and in particular to treat their pain, basically we talk about we need a bidirectional neural interface. So we need a technology that is able to write into the neurons and to read from the neurons at the same time, and the data analytics has to be done at the same time. So up to today, there is very limited success to record the neuron signals and stimulate neuron signals at the same time from the same location. I think even Medtronic doesn't have such technology to support both recording and stimulation from the same electrodes. And we have not accidentally, we spent many years to solve this problem, and we have clinical data to show we are able to stimulate and record it from the same electrodes. As you can see on the right side, that's a human data. So each line here is a stimulation. The artifacts, as you can see, is very brief. Here's a zoom-in view. That's a stimulation artifacts we have. After each stimulation, there was an artifact of about a few milliseconds. Then after the few milliseconds, we're able to record the signals from the light-free electrodes and the cold-free electrodes. We feel very proud about this feature because we feel this feature would pave the way for future closed-loop personalized neuromodulation therapy. That would be applicable to multiple clinical populations, including Parkinson's disease and the pain and the people with depression. So then after we showed you the data, you can see here's another video. So this video is very hard to do. So if you Google online, you will see many videos of the amputee subject using a prosthetic hand to grasp some solid item, right? Typically a glass of wine or something like that. But here, as you can see, those are plastic papers. So it implies if there is insufficient strength, you will not be able to lift one cup or 2 cups or 3 cups selectively, right? And however, if there were too much strength, too much pressure, there would be a dent, right? So this task compared with some other videos you can see on YouTube, the level of difficulty is totally different because it requires you have the precise amount of control in order to lift the 1, 2, 3, or 0 cups. And that kind of control is due to we perform stimulation to, therefore the patient will be able to understand whether the fingertip is touching a cup or not. So here's another video.
This one. 2.
Lighter.
Next.
Same.
So basically through nerve stimulation, our patient is able to differentiate the weight. Basically the patient can reliably differentiate the 50 grams weight.
Okay, that's vertical. Horizontal. That's 45. It's vertical. That's 45.
So So basically, in the second video, you actually see by electrically stimulating the right nerve, actually the right fascicle with the right parameters, we can allow the patient to understand there was something touching his thumb, and can even sense the orientation of that, in this case, the rod. So we also treated our subjects residual limb pain. So you can take a look on this video.
Talk about the first thing that comes to my mind is residual limb pain. It's a huge issue for me. It is something that nobody addresses, nobody knows how to address. Until you put a sensor in somebody's arm, I think at this point, there is no way to tell if someone's pain is actually quantifiable. Okay? With this system, we were able to see that my pain was quantifiable and do something about it. And it's a huge life improvement. It improved my quality of life almost immeasurably, 1,000%. Like, I mean, I was walking around all.
So basically, through electrical stimulation, we could treat our patient's pain. And after this patient has been explanted, even after the explant surgery, his residual limb pain is still much lower, dropped from 7 initially to right now about 3. So after we deliver the motor, the restored part of the motor function and the sensory function as well as treating his pain, as you can imagine, he was a free range amputee before the explant surgery. He could use the elevator, then he could shake hands with others. He could use a computer keyboard, and he was very proud of the work and to be part of the team. So here are some patients' feedback. So the patient really feel if we keep working on it and keep working on it, there was a way to create a new hand for the amputee population. And secondly, is the patient really confirm our technology is a mind reading technology instead of a pre-programmed grasp pattern. Basically, it can understand the intention and act accordingly. So the summary is right now we have shown the ability to control individual fingers in transradial amputee. I think we're so far the only team can do this. And secondly is we demonstrated the AI model once being established, it can persist for at least 3 months, maybe even longer. So meaning of the 3 months, the patient should come back to update the AI models. And the user reports near natural finger control. And so far we are able to treat some other conditions like to restore some sensations and treat the pain through high precision electrical stimulation. So in the future, we hope to establish a collaborative platform to support further research, in particular how to involve multiple academic labs and involve companies to push this research efforts further. Secondly, so we need to develop a fully functional, a complete implantable system technology and a software. So, and also the training paradigm is a lot of work. And thirdly, so we needed to conduct a clinical trial with more patients to get the FDA clearance. It's a class 3 medical device, so you can imagine the kind of resources required and the efforts required in order to get FDA approval. So that's our view of the future brain-machine interface. I really feel let's say in the next 50 or 100 years, maybe we could see the amputee subject being able to play a piano just as well as I can possibly do. I don't know how to play pianos, but I think at least as well as I can. So far, this work has been done by the contributing members, including University of Minnesota and the UT Southwestern Medical Center. The technologies are pretty much done at the University of Minnesota, and the surgery and the medicine, they are done at the University UT Southwestern Medical Center. And in order to further the research, I set up a small company with the collaborators here Its name is Fascicle. So we hope to deliver, to commercialize the technology and deliver products to our patients. So far, here's the last slide, the acknowledgement. The PIs on this project have been collaborating for more than 10 years, including myself working on implantable devices, and Ed Kiefer, and he's a physiologist and a material scientist, and Jonathan Chen, and he's a fine neuron surgeon, and my wife Catherine Chizang, she has a computer vision and machine learning background. So the clinical portion of the research was supported by DARPA and led by Edward Kiefer. And the technology portion of the research was primarily developed in my lab. So the circuits, the hardware were developed when I was at the National University of Singapore. I had 7 projects. Then after I came to Minnesota, this project was supported by NSF and NIH and some DARPA supporting as well. And recently, this research is being supported by our company, Fascicle. And here's a conflict of interest declaration. So I'm a co-founder of Fascicle. I'm its president, and Fascicle is a sponsor of the research, and the interest has been reviewed and managed by the University of Minnesota in accordance with its conflict of interest policy. So thank you very much. Please let me know if you have any questions.
Thank you. Great talk.
Thank you.
Questions?
Zhi, very interesting talk, very impressive results. I wanted to ask you about, so when you detect the neural signals, the nerve signals, and control the fingers, is it primarily a binary control, or is there some quantification needed between the neural signal and how much the fingers move?
Yeah, so Roger, very, very good question. So in our case, it's a continuous decoding, meaning every 50 milliseconds, the decoder is going to output the joint position. And we have done some quantization around 128 different levels. So in short, yes, it's continuous decoding with high accuracy. So it's not a binary.
Okay.
It's not a open or close. It's not open close. It's continuous. Otherwise, the patient wouldn't say it's natural. But you're absolutely right. It involves a lot of feedback, because the patient can keep adjusting his or her intention until it's a continuing it's continuous decoding.
So basically, they see what is happening with their eyes, and then they keep changing their intention.
Yeah, in 95% of experiments, it's something like that. In some experiments, we ask the patient to close their eyes as well for some other studies. But the 95% of studies, yes, they look at their hands to do the test. Yeah.
Okay. So if they close their eyes, then they're using tactile feedback, basically?
Yeah, they have to rely on their feedback. So one is they need to understand, basically, if you want to move your finger, your intention actually should be able to specify where you want your finger to stop, right? Right. Yeah. So one is related to how accurate you can decode that intention string, and secondly is in some cases we provide the feedback when we have an electrical stimulation. Do you remember the patient grab the plastic cap? Sometimes they grab a paper cup as well. So that requires a fine control. In that case, it's driven by feedback.
Okay.
Yeah.
Can I ask a question? Zhi, can you tell from the signals that some signals could be personalized for every individual, but there's some signals that could be generalized for most people? Is it possible that the decoding, there is some generalized decoding, and then you can put on top of it the particular for each one for each person?
So sad. That's a brilliant question. we have been keep trying that route for multiple months, and we realized that sad, you're right. I think it would be very helpful if we can establish a bigger neuron data from multiple subjects over multiple days, right? Then that would make the training of the model a lot faster and make the model more reliable. So you're very, very right. And it depends on the task. For certain tasks, like to differentiating the weight, to mapping the weight to the right stimulation parameters and to trigger that specific sensation, we realize that it requires a small amount of training, and the data can be very much generalized in that case. And for motor decoding, it's yes, some data, yes, we still feel it's slightly tricky because different patients, they have different conditions. The implantation location is different. The signals would be more or less different, but you're right. We still use the data we established from previous subject as the initial model, and then to evolve, to be updated by the data. Thank you. I don't know how to describe this. I don't exactly know how to describe our feeling because it's not really in the literature. So good question.
Thank you.
So what about the phantom feeling that a lot of amputees did you?
You're talking about the phantom pain and the phantom sensation,
and
right?
the interference that may happen.
So Nicholas, that's a very good question. We so for the subject that we have worked with, they do not have a phantom pain, phantom sensation, because that kind of a sensation disappeared of the period of the few years, right? Our subjects, they have been amputated for like 5 to 10 years. So, but I do think by performing electrical stimulation, I think the phantom sensation can be treated. We just needed to stimulating the right nerve with the right stimulation parameters, and that phantom sensation can certainly be treated, just like a pain. Pain is a sensation too, right? So.
Thank you.
Hi, Professor Zhang.
Yes.
Hey, Professor. Sorry, I have a small question.
Yes.
So for your online model, what kind of GPU you are using? So it's some kind of mobile phone based or other kind of?
So we have multiple online models. So the most elaborated model were trained based on 10, 15 GPUs. So each GPU handles one joint. So we have 15 joints, sometimes 10 joints. So then we have 10 or 15 GPUs. I couldn't recall the exact GPU model, but I do remember we purchased the GPU, a new set of GPU in 2019. Then we just bought the best we can possibly find. So
okay.
So then very recently, after it's related to the question Sad just asked, we realized that the model training can be simplified if we have a large data. So very recently, for most recent patient, we're using a microcomputer to perform the decoding. The microcomputer is like this large, and we have added a wireless and added other device into the microcomputer. So the microcomputer is embedded into the patient's arm. Of course, you would anticipate some performance drop, but that's a promising direction in overview.
Actually, I was asking about for the real-time inference, not for the training process. I mean, after the training, you have to deploy the trained model into the implant module.
Yeah, it's always inference. I refer to inference as well. So the training would take a much longer time, right? In any case, we have to, even for the inference, it's non-trivial because of that.
So you mean for the inference, after the training, you still need several CPU to work?
So for the most elaborated model, yes. because you have to imagine, even to do inference, it's we have to do a full round of neuron signal processing, front-end signal processing, and after that to get something can be handled by deep neural network, right? Even
so does it mean? Sorry for the interruption. So does it mean that they have to stay at a certain position, certain location to use the hand, use the artificial hand?
In our study up to 2019, yes, the patient have to sit on. The patient is not able to move around until this year or close to the end of 2019. As you can see, I talk about free range amputee, right? In that case, because of the inference can be done within a portable device. So our current amputees can move around. They can go to mall. They can take a train.
So for your latest development, does it mean that you are using a similar model or?
Yeah. So just back to what the setter asked, we realized that the data from multiple patients could be used to simplify the model development and also to simplify the inference as well. So therefore, we're using a simplified model. It's also, you have to understand, when we first started this project, there was a very little hardware infrastructure support, and over time, we also learned to improve our algorithms to make it better support our patient needs.
So you mean currently you just need a very small board with a very small CPU, GPU?
So we're using an NVIDIA microcomputer.
Okay.
Yeah.
It means it's like a TX2, something like that?
I do not know. I have to check with our engineer.
Oh, okay, that's fine. It's just
so
embedded platform.
Yeah, what we did was we investigated a few deep neural network accelerators done by Google, NVIDIA, and one more company, Intel, and finally we decided to go with the NVIDIA platform. We did a lot of modifications to that platform, but yes, currently the amputee subject is served by that device, like this size.
Oh, yeah, it's good.
Including the fan.
And another related question is that, sorry about my long questions. Another question is that about the sensory feedback. I can see that you just show us the feeling of the center of the pen, and also the feeling at the thumb, right? To sense the weight and also the orientation, rotation of some objects.
So that's a difficult task because there were a lot of sensory receptors on the human hand, right? So scientifically, it's very important to deliver a localized, discrete sensation, and there were very different sensations, like implied as well. There were so many different sensations. So right now we're sure we can deliver localized sensation with maybe centimeter resolution, not like a millimeter resolution, centimeter resolution, and the location of the sensation, according to the patient report, is distributed at least more than 50% of the hand, maybe 70% of the hand. So basically, by stimulating with different electrodes, different parameters, you can trigger a localized, discrete sensation. It's a tough problem.
Yeah, actually, I have seen some kind of related research on the artificial skin. Actually, I think it should be closely related to your work or your research, right?
Mm-hmm. Yeah.
Thank you. Great
Thank
work.
you.
Thank you.
Thank you, Bing. Any other question? So thank you very much. Let's give another applause. Have a great weekend.
You too, guys. Thanks.
And you'll keep hearing from us for the next one.